Aditya, should we start? Okay, you sure? Okay, so today's sessions, I had asked you all on the group whether we should continue with the next chapter, should we do some tutorials. Some of you all had said that we'll do tutorials, the others did not respond. So what I thought is we will take up some tutorials of the previous chapter. Am I audible? Is my voice clear? Can someone tell me if my voice is clear? Okay, great. So what I thought is since today we had two lectures, we'll start with a new chapter, and on some day when we have a single lecture, I will take up a tutorial of the previous chapter, just some solving of problems. Okay, for now the pace of the lectures which are going is quite okay. If you all have some difficulties and all that, please see that you all slow me down. Otherwise, I will start going really fast. Okay. So anyway, this is not very difficult. I doubt you're going to have much problem with this. So let's continue. So let me tell you what we are going to study in this chapter. So in this chapter, we will look at. I think I have included the wrong file. Just let me include the correct file. Sorry, this is a. Here it is. That's the same. Okay, so in this chapter we will study some arithmetical functions. Okay, is anyone familiar with what is a arithmetical function? You all have studied arithmetical function, or you all might have called them number theoretic functions in TY. Can someone tell me what is an arithmetical function or a number theoretic function? Can someone just switch on your microphone and tell me what is a arithmetical function or a number theoretic function? You all have most probably studied it as a number theoretic function, which are the same, they're just two different words. Can someone switch on your microphone and tell me what is a arithmetical function? Yes? Is anyone familiar? Okay, so can you at least type and tell me whether you all know what is an arithmetical function or a number theoretic function? You can type yes or no, there's no problem. I at least want you to communicate with me. So Simran has said that a arithmetical function is a function which is defined on the set of natural numbers. And that is correct. That is what a arithmetical function is. There are many terms you use for these, but that is basically what an arithmetical function is. Sometimes you call it a sequence also. Okay, so these are all different terms for the same object. So herein specifically we will look at real and complex valued functions. So arithmetical functions for us, or number theoretic functions, we will be using the term arithmetical functions, are real or complex valued functions defined with a set of positive integers. That means functions going from n to either r or c. So these are arithmetical functions. Uh, can anyone give me some examples of arithmetical functions? Can you put on your mic and give me some examples of arithmetical function? In combinatorics also we have looked at a few arithmetical functions. Can someone give me some examples of arithmetical functions? You can even make up your own functions. You will generally land up with something nice. Can someone give me some examples of arithmetical functions? You just need a function that goes from n to ROC. Can someone please tell me some examples of arithmetical functions? Yes. See, I will have to talk. Okay, that's right, Mukta. So one arithmetical function which you can have is f of n equals n itself. Simran has said it generally use the variable n since we are going on n, but f of n equals n square. That is also an arithmetical function. You can have something as simple as f of n equals 0 or f of n equals 1, a constant function that goes inside the real or complex valued set, real or complex set. So that is as simple as that. Those are arithmetical functions, nothing very difficult. Well, I've seen many things like in analysis also, n goes to 1 by n when you talk about convergence, or n goes to 1 by n square and things like that. We will not be interested in these arithmetical functions. We will be interested in some other specific arithmetical functions in this chapter. So in this chapter, we will be considering certain specific arithmetical functions, which you should remember these arithmetical functions because we will be studying them in detail in the next two chapters. Their properties are very interesting, so we'll be studying them in the next chapter. I'm sure you know a few other nicer arithmetical functions which gives us some information. Example, I think all of you all are familiar with the Euler's function. That is n goes to phi n, where phi n is the number of integers less than n and relatively prime to n. This is also an arithmetical function. Phi is an arithmetical function. Or I think you all are also familiar with the function mu, though you all might not remember the definition, but the function mu is also an arithmetical function. Okay, so you can also have another interesting function. You will see that this is interesting later in the chapter. That is, you can take n. What should I? There is a specific notation for it, but anyway, I will take n to, let me call this as g for now, but later on it has a specific notation. So g of n is 1 if n is 1 and 0 otherwise. So this is also an arithmetical function. Okay, so you will see many arithmetical functions as we proceed. These are basically, but we are interested in just a few. Okay, so the first one which we are interested in is mu itself. Okay, so how is mu defined? So mu of 1 is defined to be 1, and for any prime factorization of n, if this is the prime factorization of n such that a1, a2 up to ak are all equal to 1. Remember that the prime factorization is unique, so we can use the prime factorization to define a function in this manner. So if all of them are 1, these numbers are called as square free numbers, okay, where the powers of the primes of the distinct primes are all 1, these numbers are called as square free numbers. So if a number is square free, then it is -1 raised to the number of primes in the number. And if in any other case it is 0. Can someone tell me, switch on your microphone and tell me what is mu of 100, what is mu of 10? Just to know if you have understood what is the mu function. Can someone switch on your microphone and tell me what is mu of 100 and what is mu of 10? Yes. Can you please, someone please switch on your microphone and tell me what is mu of 100 and what is mu of 10? Aditya? Yes. Aditya, can you tell me what is mu of 100 and what is mu of 10? Yes, why no? See, it is very easy. You can tell me definitely. If n has all distinct primes, power of the powers which appear here is only 1. What is the prime factorization of 100? Can you tell me what is the prime factorization of 100? Aditya? Aditya, can you tell me the prime factorization of 100? Aditya, you can switch on your microphone and just tell me what is the prime factorization of 100 and what is the prime factorization of 10? Come on. Aditya, you know the prime factorization of 100? Can you all hear me? Okay. What about Akshata? Akshata, can you please tell me what is the prime factorization of 100? You can type in the chat box that list. Yeah. What is it? Akshata? What about the prime factorization of 10? Yeah. So can you tell me what is mu of 100 and mu of, yeah, that's right, 2 and 5. What is what is mu of 100 and what is mu of 10? Look at the definition and tell me. That's right. And mu of 10? That's right. So mu of 10 will be -1 raised to 2, which is 1. Okay, thank you, Akshata. Okay, so this is how you define the function mu. So everyone should be clear with this. So you can see that only numbers which are square free, these numbers are called square free. Numbers like 10, you can, examples of them are like 2 into 3 into 5, or 3 into 5 into 11, Things like this are square free. There is no square number which divides it. That is called as a square free number. Okay, so get used to these terms since we are doing number theory. So remember the definition of mu. It's a very interesting function, as you will see later. Okay, so we will prove that this sum is something which we are going to be interested with many times. When we write summation d divides n f of d, what we mean by this, we mean d varies over the divisors of n. So example, if n is 100, let me put, if n is 100, this will be, we know that the divisors of 100 are 1, 2, 4, 5, I hope I'm not making a mistake, 5 square, which is 25, 10 and 100, 50 and 100. I don't think there's anything else. So if I'm making a mistake, you can just tell me. So this will be f of 1 plus f of 2. We are only looking at positive divisors, plus f of 4 and so on, plus up to f of 100. Okay, it's a finite number, but I'm not writing everything. I think you have understood. Oh, 20 is also there. We have 20 also. So anyway, whatever the divisors of 100 are, it is the sum of all of those. In fact, you can look at the divisors by just looking at the prime factorization. The moment you know the prime factorization, you can see what the divisors are. Okay, so this is that sum here which we are going to be looking at. This is a very important sum for us, and let's see what this is. See, this is the greatest, this symbol which you can see here is a symbol for greatest integer. Okay, this symbol here is a symbol which you are going to use for the greatest integer. So greatest integer less than or equal to x. So we know that any real number lies between two natural numbers, say n and n plus 1. So the greatest integer of x will be the one which is on the left, it is n here. Okay, so that is your greatest integer function, and I'm sure everyone can see this equality here. Okay, try to understand this equality, it's not very difficult. If n is 1, then you're going to get 1 upon 1, which is 1, and the greatest integer of 1 is 1 itself. If n is greater than 1, then you're going to get a number less than 1. So the number is going to lie, 1 by n is going to lie between 0 and 1, right? It's not even going to be 1. So any number that lies here, its greatest integer is going to be 0. So the right side equality, this part of the equality is clear. Okay, so this is what we want to prove. We are going to prove that summation d divides n mu of d is 1 if n is equal to 1 and 0 otherwise. It's a very simple proof. There is nothing difficult in it. So basically what we need to know is, if n is 1, what are the divisors of 1? Obviously the only divisors of 1 is 1 itself. So summation 1 divides 1 mu of, or d divides 1 mu of d. This will only be mu of 1, and by definition we know that mu of 1, here you can see mu of 1 is 1 itself, so this will give us 1. Now what happens in the other cases? So suppose n is greater than 1, then we know that n has a prime factorization. Say p1 raised to a1 into p2 raised to a2 up to pk raised to ak. So summation d divides n mu of d. Now what are the divisors of n going to look like? So the divisors of n are going to be of the form, the divisors, okay, they are going to be of the form d equals p1 raised to b1, p2 raised to b2 up to pk raised to bk. This is very basic number theory, where your bi's lie between 0 and ai's and ai. Okay, so this is what the divisor of n is going to look like. Okay, so now we have to know, we know that the mu of only square free numbers are what come into play. If a number is not square free, then mu of that number is 0. So we only need to bother about the divisors of mu which are square free. So what are the divisors of mu which are, sorry, the divisors of n which are square free? What are the divisors of n which are square free? The divisors of n which are square free are going to be p1, p2, p3 up to pk, then p1 into p2, p1 into p3, and so on. So it's going to be this form. So firstly 1, so mu of 1 plus, you have the distinct primes, that is I going from 1 to k, mu of pi plus summation two distinct primes. So we can write that as 1 less than or equal to I, strictly less than j, less than or equal to k, mu of pi times pj. Okay, plus let's write the last one, that is mu of p1, p2 up to pk. So you have only a single choice. Okay, I hope everyone can see why this sum becomes this. That is, we are only bothered about the square free integers, but mu of 1 is 1, mu of a single prime is going to be minus 1 raised to 1, which is minus 1. So this will be k times minus 1 raised to 1 plus, here you have, now how many terms appear here? You're going to get exactly n kc2 terms. So kc2, because you're choosing 2 primes, minus 1 raised to 2 plus, in the third part you will have 3 primes, that is kc3 minus 1 raised to 3 plus up to, here you have minus 1 raised to k. Can someone tell me what this expression is? I'll make it a little easier for you. This k here is the same as, write it, it is the same as kc1. Can someone tell me what this expression is? You have learned combinatorics, so you can very easily identify this. Can someone turn on your microphone, tell me what this expression is? See, you're looking at the binomial coefficients here, kc1, kc2, and so on. So you have to think about this here, you can think as kck, and we know that 1 is kc0. So what are you looking at? When you look at binomial coefficient, the first thing that comes to your mind is the binomial theorem. Okay, so if you look at this carefully, this is just 1 plus minus 1 raised to k, and 1 plus minus 1 raised to k, as long as k is as long as k is not 0, which it is not, since someone, okay, so as long as k is not 0, this is going to be equal to 0. 1 plus minus 1 is 0, 0 raised to k is 0. So we can see that this sum is equal to 0. So this proves our theorem. Okay, so now we will define the Euler-Totian formula, which you are already, the Euler-Totian function, which again you are already familiar with, so I don't need to say anything. So for any n greater than 1, phi of n is the number of integers less than or equal to n and relatively prime to n. Okay, therefore phi of 1 is writing the Euler-Totian function for first few integers. This will be 1. I purposely put less than or equal to. Equal to is only relevant when n is equal to 1 itself. Phi of 2 again is 1 itself. Only 1 is relatively prime to 2, 2 is not relatively prime to 2. Phi of 3 is 2. Phi of 4, what is phi of 4? 1 is relatively prime to 4, 2 is not relatively prime, 3 is relatively prime, so this is again 2. And what we go out to do, I think all of you are familiar with the formula of the Euler-Totian formula, the Euler-Totian function, but we will still prove it, and I think the proof which we will be giving in this course will be slightly different from the proof which you have seen in combinatorics. I think I had used, if I'm not mistaken, I proved this theorem in combinatorics. So we will first prove this formula here to get to the proof. Try to keep focused to what we are doing. I'll give you a break in the middle so that you don't get too tired. So let's take S to be the set 1, 2 up to n, and I'm going to partition S in a very nice manner. Okay, so this is the set 1, 2 up to n. I'm going to partition S in a very nice manner. So for every divisor, d of n, I will let AD, okay, be the set of all k in S such that the GCD, see the GCD of two numbers, so the GCD of k and n is D. Okay, I hope you can see that S is in fact ADs, these different ADs are going to partition out S. Let me elaborate it with a small example. I think that will be nice. So let's look at 10 itself. So what I'm saying here is, I'm saying that S is going to be equal to union D divides N AD, and none of these ADs are going to intersect. That is very clear because for different Ds the GCD is different, and that cannot take place. You can't have K1 and K2 where GCD of K1 and N is D1. You can't have K such that GCD of K and N is D1 and also D2. That's not going to take place. So GCD is a unique integer. So yeah, let's look at the case when N is equal to 10. So S will be 1, 2 up, 3, 4, 5, 6, 7, 8, 9 and 10. What are the divisors of 10? So the divisors of 10 are the divisors is 1, 2, 5, 6, 7, 8, 10. Okay, let's look at the different ADs. So your ADs are, so what is A1 in this case? It is the integers which are relatively prime, the integers in S which are relatively prime to 10. So that is 1, 3, 5, 6, 7, 8, 9, and that's it. What is A2? A2 are the integers such that the GCD is 2. So that is the GCD of 2 and 10 is 2. The GCD of 4 and 10 is also 2. So 4 comes here. Hope everyone can see that. 10 is 2 into 5. So the GCD of 4 and 10 is 2. The GCD of 6 and 10 is also 2. 7, 8 and 10 is also 2. 9 and 10. That's it. What about A5? So I want the numbers whose GCD with 10 is 5. So firstly, we're going to have 5 in this and nothing else. And A10 is 10 itself. So if 10 and 10 is 10 and nothing else can give you 10. And what you can see here is these AIs partition out 1, 2 up to 10. You see 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So every integer comes in one of the AIs and they are all disjoint. So this is quite clear. Now the intention will be, so you can see your S here is going to be a disjoint union D divides N AD. It's a disjoint union, and since it is a disjoint union, what happens is the cardinality of S, which is N, I hope everyone can see that the cardinality of S is N, will be, this is a disjoint union, so this will be summation D divides N cardinality of AD. So now we are interested in catching hold of the cardinality of AD, and we do it in a very interesting manner. Okay, you look at the set XD. So take the set XD to be the set of all the integers, all K, such that there are two conditions. Or should I use, I think I should use another notation instead of K. Let me use T. T such that GCD of D is a divisor of N, so GCD of divide that, yeah, Tn N by D is 1, and your T lies between 1 and N by D. Okay, hope everyone can understand what this set is. You're taking the set of all those points, okay, which are relatively prime to N by D, so less than N by D and relatively prime to N by D. So the set of all points which are less than N by D and relatively prime to N by D. Can someone tell me what is the cardinality of XD? Can someone switch on your microphone and tell me what is the cardinality of XD? XD is a set of all those points which are less than N by D and relatively prime to N by D. Can you tell me what XD is? See, I want to have a feeling that you are around, so you need to talk to me sometimes. Can someone please switch on your microphone and tell me what is the cardinality of xd? Yes. Simran, do you know the answer? What is the cardinality of xd? Simran? Are you sure? Just look carefully and see. I'm sure you know the answer. It's a set of all those integers which are less than n by d and relatively prime to n by d. There's a notation we have for this. What is it? Okay, this is clearly, I don't know whether you missed it, but this is clearly phi of n by d. This is what the cardinality of xd is. Okay, this is phi nd. We are going to show that AD and XD are bijective. Okay, we are going to prove that AD and XD are bijective. So let's define a function f from AD to XD by f of, okay, where is that AD? F of k equals, there's a natural way of defining this, f of k equals we want it to be, so I know that the GCD of k by d, okay, k by, yeah, I think this will work. Let's just check. So take f of k to k by d. So firstly, let's see that this actually makes sense, that this definition actually makes sense. Now, yeah, I actually should suffix d here, but I will not do that. I have done it in your notes, but I'm not going to do that here. It will make my work difficult. So I'm going to show that this is a bijection. First, I need to prove that this function is well defined. Okay. So what is the meaning of this function is well defined? Here, there is no proper problem in the notation, but I better know that this k by d lies inside xd. Okay, so that's what I mean by saying that this is well defined. So suppose k is in, so what I need to basically show is, if k is in AD, then k by d is in xd. So suppose k is in AD. What is the meaning of this? By the definition of AD, what does this mean? You can see here. It means that the GCD of k and n is d. So this means that the GCD of k and n is equal to d, which means that, see, you can see here, so this will mean that the GCD, this is basic number theory, of k by d, which makes sense, and n by d, d is a divisor of k, so this k by d and n by d makes sense. D is a divisor of k and it is a divisor of n, so you can talk about k by d and n by d. This will be equal to 1. If you're not familiar, if you're not convinced about this, I'll give you a fast proof at the side here. Since GCD of k and n is d, there is some x and y such that kx plus ny is equal to d. Now d divides k and d divides n, so we can talk about k by d and n by d. So this gives us k by d times x plus n by d times y equals 1. Okay, from here this expression you can tell the GCD of, from this expression you can tell that the GCD of k by d and n by d is 1. Okay, that is because k by d times x plus n by d times y is 1. That is because suppose you have some other divisor, say some notation t. Say suppose t divides k by d and n by d. If t divides k by d and n by d, then t will also divide 1, which means that t will have to be equal to 1. And this tells us that the only possible divisor of k by d and n by d, common divisor, is 1, which means that the GCD of k by d and n by d is 1. So the GCD of k by d and n by d is 1. Also, we know that as k lies in AD, k lies between 1 and n, which means that this will hold true, and dividing throughout by d, we will get 1 by d is less than or equal to k by d less than or equal to n by d. Okay, and I know that k by d is an integer, positive integer, so this will tell me that this is greater than or equal to 1, this is greater than or equal to 1, less than or equal to n by d. So this tells me that k by d lies inside x by d by both of this. What is x by d? You can see again, it is the set of all those points which are relatively prime to n by d and less than n by d. So this tells us that the function is well defined. The only other two things which I need to prove is that this function is 1 1 and on 2, which is very simple. Okay, I think 1 1ness I will not even prove because it's that easy, so that I will leave out to you. 1 1 I'm sure all of y'all can do. This y'all will do. That's because if suppose f of k1 is equal to f of k2, it basically means that k1 upon d is equal to k2 upon d. Cancel out the d on both sides, you get k1 equals k2. So you can prove this on your own. 10 standard. Okay. 3rd standard. Okay. Why is it onto? It is onto because you start with any suppose you start with some t inside xt. I want someone to give me the pre-image of t. What is the meaning of this? This means that GCD of t and n by d is 1. Can someone tell me what you think is the pre-image of t? It's quite natural. What is the pre-image of t? Switch on your microphone and tell me what is the pre-image of t. F of what gives me t? F of what here gives me t? There is only one option. The only thing is to check whether that option is correct. There is no other possible option. By the definition of the function, you can see that there is only one natural option. Can someone tell me? Yeah. F of? Yes, Simran? Yeah, that's right. So the pre-image of this is TD, that is the natural option. Okay, so f of TD is T, so that is the natural option. But for this to be true, because f of TD would be TD upon T, TD upon D, which will give you T. But for us to be sure of this, we should know that TD lies inside AD. Okay, we should be able to say that TD lies inside AD, which is not so difficult to see, because T comma n by D is 1. Okay, this tells us that from here, this tells us that the GCD, this is just very basic number theory. If you are not familiar with this, you should maybe read up, or you can ask me, but I will not prove these things in detail here. Okay, so GCD of TD and N will be D. You can very easily prove this. Okay, so GCD of TD and N is D, and also as T lies between 1 and N by D, because T is in XD, multiplying throughout by D, we will see that D is less than or equal to T, less than or equal to N, TD. Okay, and this we know is greater than or equal to 1. So therefore TD lies between 1 and N, and GCD of TD and N is D, which means that we know that TD is in AD, and f of TD is T itself. F TD is T itself, and therefore the function is onto. So this is a 1, 1 and onto function, and I'm going to need to erase again since I have not kept enough of space. So now the proof is essentially done. Since f is a bijective function, the number of elements in XD and AD are the same. So therefore number of elements in XD is the same as the number of elements in AD. So what we have here is simple observation. N is the number of elements in S. So you can go back and check. This is what I had defined S to be. But S we had broken up into a partition of ADs, cardinality of AD. But the number of elements in AD is the same as the number of elements in XD. So this is cardinality of XD. Now I had told you that the cardinality of XD is phi of N by D. Okay, and from yesterday I had done this, I think, yeah, yesterday or the day before that I had told you this, that as D varies over all the divisors of N, N by D also varies over all the divisors of N. In fact, if you look at the set of all divisors of N, say call it as, I should not use X since I have been using it often, say suppose D is the set of divisors of N, there is a natural bijection from D to D. This is the set of divisors of N. Okay, there is a natural bijection which is f of D equals N by D. Okay, I had called this divisor as the complementary divisor to D. Okay, so here what you see is for every divisor D, or you are going N by D, which is the same as, so this is in the opposite direction. Here you are going from down to up, you can go from up to down in this particular manner. This is something which we will be using often. Okay, so this is the same as summation D divides N phi D. So N is summation D divides N phi D. Very nice proof to this theorem. Okay, let's look at the next theorem statement. If anyone is tired, please tell me. We will stop for 15 minutes and then continue. Okay, if you don't talk to me and don't tell me, I will just continue. Okay, so let's prove that phi n is equal to summation D divides N mu D times N by D. To prove this, let's start with the right hand side sum and prove that the right hand side sum is equal to phi n. Okay, so summation d divides n mu d. Sorry, I think we don't start. Sorry, we need to start with phi n itself. Yes. Okay, there is a nice way of getting this. Okay, so phi of n is a nice trick to this. Well, let me just write first summation k going from 1 to n 1 upon the GCD. This is a nice interesting way of writing this. N comma k. Let me just write this as, yeah, I think that's better. Okay, so why is this true? Okay, so why is this sum here true? That is because, let me again, I think if I take an example, it is easier to observe. See, the GCD of two numbers is going to be, when is this number 1 and when is it 0? This number here, 1 upon the greatest integer 1 by some number, is going to be 1 only if the denominator is 1. If the denominator is anything greater than 1, it is going to be 0. Okay, so you can see that 1 is only going to contribute, you're going to get a 1 only when k is relatively prime to n. Let's again take an example and see exactly what is happening here. So what I'm saying is phi of 10, it's nice to take an example and see, then it sticks with you. K goes from 1 to 10, greatest integer of 1 upon GCD of 10 and k. Okay, so let's see what this is. So when k is 1, the GCD of 10 and 1 is 1. So the first term is going to be 1 upon 1, which is 1 itself. When k is 2, 2 is not relatively prime to 10. 2 is the GCD of 10 and 2 is 2 itself. So you're going to get the greatest common integer of 1 by 2, which is 0, plus of 3, you're going to get the GCD of 10 and 3 is 1, so 1 upon 1, which is 1 itself. So what you can see is we are adding up all the numbers which are relatively prime to, we are adding 1 for every integer which is relatively prime to 10. Okay, so you can see that. Now, what is the greatest integer of 1 by n? 1 over n. We have proved earlier that the greatest integer of 1 over n is summation d divides n mu d, right? So this here is going to be the double sum, summation k equals 1 to n. Okay, and this part here will be summation d divides the GCD of n comma k, okay, mu of d. Now there's one simple observation here. D will divide the GCD of n and k if and only if d divides both n and k. So this you can write as summation k going from 1 to n summation. I hope that is clear. If d divides the GCD of n and k, then we know that the GCD divides n and k, and therefore using the transitivity we know that d divides n and d divides k. Similarly, if D divides N and K, we know that the GCD of N and K, that's not similarly, but GCD of N and K is a linear combination of N and K. So therefore, if D divides N and K, then D will divide the linear combination, which is the GCD. So D divides N, D divides K, mu of D. Okay, so this is what we have here. Now, the question is, how many times for each divisor, okay, how many times each mu D appears? Okay, the question is how many times each of these mu Ds actually appear. In this double sum, how many times each mu D appears? So that is the basic question which we need to tackle. Okay, I don't know whether I should do this with an example. Yeah, I think I should describe it. I should look at the sum using an example. Let's look at this double sum here. Let's take again 10 itself. So summation K equals 1 to 10, summation D divides K, D divides N, mu of D. Okay, so what are the different possible values for D? So D can take the values, because K runs from 1 to this is 10, so D has to be a divisor of 10, so it can take values 1, 2, 5 and 10 itself. So these are the different. Now, how many times does each mu D appear? Okay, how many times does each mu D appear? So how many times will each mu D appear? So here you can see that how many times will mu1 appear? Mu of 1. That is when for D equals 1, how many times it will appear? It will appear whenever K is a multiple of D. That is, in this case, for all multiples from 1 to 10. So mu of 1 will appear 10 times. Okay, because when you can check here, when K is 1, you're going to have 1 will divide K and 1 will also divide 10. When K is 2, 1 will divide K, 1 will divide 10. When K is 3 and so on. So for all the numbers from 1 to 10, mu of 1 is going to appear in this particular sum, so all 10 times. Okay. Where will mu2 appear? Mu2 will appear whenever 2 divides K. Now, among how many points from 1 to 10 does 2 divide? That is the number of multiples of 2. That will be 2, 4, 6, 8 and 10. So among all these points from 1 to 10, mu2 is going to appear in 2 when K is 2, when K is 4, K is 6, K is 8 and K is 10. That is the multiples of 2. So it's going to appear 1, 2, 3, 4, 5 times. What about mu of 5? Mu of 5 will appear when K is a multiple of 5, okay, which is just twice, that is for 5 and for 10, and mu of 10 will be once. Okay, so this is your sum essentially becomes that. So how do I know how many multiples are there of k? How many multiples are there of d from 1 to n? Can someone tell me how many multiples are there of d from 1 to n? From 1 to n, how many multiples are there of d? Can someone tell me how many multiples are there of d from 1 to n? This is essentially going to be summation d divides n mu of d. This is what we saw, mu of d times the multiples of d, the number of multiples of d from 1 to n. Okay, the number of multiples of d from 1 to n. What are the number of multiples of d from 1 to n? Can someone tell me? How many multiples are there of d from 1 to n? Can someone switch on your microphone and tell me? And that too, d is a divisor of n, so it's even easier. How many multiples are there of 2 from 1 to 10? So you have 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. What are the multiples of 2 from 1 to 10? It's 2, 2 times 2, 2 times 3, 2 times 4 and 2 times 5. You have 2 times 1, 2 times 2, 2 times 3, 2 times 4 and 2 times 5. So what is this maximum number that appears here? Okay, the maximum number that appears here, you're running from 1 to something. What is that maximum number that appears here? It will be n by d. It's quite obvious. So the number of multiples of d from 1 to n is n by d. So this gives us summation d divides n mu d times n by d. That proves our statement. Okay, if you have not yet got it, you can have a look at the proof again, and I put it up. Okay, should we take a break or can we continue? Can someone tell me? Should we take a break or should we continue? If you don't respond, it means that you'll have left the phone somewhere and you'll have gone. Okay, Simran wants to take a break. Anyone wants to continue? Akshata, I don't want to pronounce your surname because I don't think I can pronounce it correctly. Akshata, can you tell me if you want to take a break or continue? I was talking to the other Akshata. Should we take a break? Yeah, that's fine. Okay, we'll take a break. So then we'll take a break and we'll come back. How long break do you all want? Yeah? Can someone tell me how long should we take a break? 5 minutes. I'll give you more than that. We'll take a 10 minutes break. Okay. You relax, have a sip of water and come back. Okay. Then we'll complete this. Okay. We'll take a break now. I will leave the meet open. You can leave it. I think I will leave the meet open though. Okay. Let's pause the recording.